Okay, welcome back, everybody. We have some chit-chatting without recording, so you guys missing it if you're not coming to the class. So as I said, today we want to focus on this new module about main memory. This would be basically what main things we're going to say today would be the basis of your third computer assignment, third and final computer assignment. One minor change that I made is the final projects. Initially, I was planning to give you an option between a cover channel and designing a simulator. With all these kind of events that are happening past 2 weeks, I was decided that it might be a little bit kind of too much, given that there are other things that might be shifted and all. So I changed it to just a simple write-up of 4 papers. I already uploaded the instructions on the website, on the class website, so just go and read it and write it. Some students wanted to still do at least a cover channel one, so I'm going to bring that option back. So in case any of you wants to do the cover channel, we can do. I'll just add it to the second part of the instruction that is already uploaded. So just wait until tomorrow and you will see the updated instructions. Yeah.
Is that in replacement of the paper?
Yeah. So either or. So you can either do the real attacks. So the cover channel one, you have to implement it on the real system. I think again, it depends. I think in terms of amount of time that you requires, probably it's not going to be that much. I think the biggest thing would be, since it's real hardware, you have to deal with noises and all. And again, it's one of those things that, depending on how much you want to spend time on it, you can make it nicer or more complicated or not. But you can probably find something bare bone and do it. Otherwise, just do the write-up. The write-up is also, I mean, it's interesting. You can go a little bit deeper into the paper, especially since we didn't really do very well on the paper presentation last 2 weeks. Given the circumstances, I think we would be giving you a little bit more options to go deeper. Okay. Any questions about that? Okay. And then the third computer assignments is out as well. You have until Tuesday of 2 weeks from now to finish it. This would be based on memory scheduling. All right. So things that we have discussed so far. So of course we started intense amount of lectures, 4 weeks. We talked about various different things in out of order execution. Then we talked a little bit about memory hierarchy and cache designs, and hopefully CA2 helped you to a little bit understand a little bit more about replacement policies. Then last 2 weeks, we did paper readings and presentations. We were kind of in the brink of World War III as well, but that didn't happen. So I'm glad that you guys are back, and it's very unfortunate that as educators we didn't provide the means for you to feel safe, to be able to kind of be a regular students and have your opinions expressed. So I wasn't feeling very well the past 2 weeks, and I think the university didn't really handle the situation very well. So on my behalf, I apologize, as I did on my on campus wide as well, and hopefully things gets a little bit better. I think personally, as someone who kind of lived with this conflict and many other conflicts in my whole life, I think the answer to these things is never violence and hate. So if you want to express opinions, you should definitely do it either way. But just make sure that never use violence nor hate toward each other. That's really never the answer. Anyway, so let's continue. So today I want to talk about memory hierarchy. And so far we talked about this thing that, oh, look, we need to actually have different ways of, different types of and tiers of memory to kind of give us the speed that we want, right? And we extensively talk about different layers of cache and how should we manage cache and all. The one that we really didn't talk about was this kind of last layer, which is the DRAM layer. or in other words, that's what we call the main memory. And this is the largest and the slowest. Of course, usually after DRAM, there's also what we call a disk. And disk is even larger and even slower. But typically, we kind of like consider DRAM and disk as kind of like one unified storage area. And then we do these tricks in the backend in order to do that. So we're going to talk about that today, and the optimizations and scheduling and all those tricks that we need to do. The second half of this lecture would be talking about security issues in memory. Specifically, we're going to talk about ROHAM memory as well, like one of the major issues in main memories. If you remember a long time ago, we talked about caches. And if you remember, we talked about things such as how do we improve miss rate, how do we improve miss penalty, how do we improve hit rate. And we talked about a bunch of different techniques. We also talked about replacement policies, and we talked about strategies to maximize hit rates. And, the basic idea was kind of like we need to evict something that is least recently used, least recently used is least useful. I mean, somehow we need to kind of figure that out. And that was kind of like what you guys tried to do in your CA number 2. And then essentially the questions that you needed to answer was, how do you select which line to evict? What should we do when we installing a new line? Should we put it at LRU or MRU or somewhere in between? And then what should we do on the hit? In other words, what should we do for promotion? And again, in your CA2, you probably play with all these 3 or some of these, and you have seen the differences, like how it can actually change your system. Okay, so now we're going to talk about advanced topics in memory systems. And I want to acknowledge that many of these slides that I'm showing after this slide is from a colleague of mine, Professor Qureshi at Georgia Tech. So what is a main memory and how is it structured? So essentially, if you look at a real system, I think this is an Intel Xeon core. As you can see here, so essentially like this is kind of like the main die. This is the CPU die. And the CPU die is usually multiple cores, okay? So in this case, this is a quad core. There are 4 distinct cores in this system, okay? And as you will see, it's usually the cache, the L1 cache of the system is like very, very close to each of these cores, okay? So the large portion of each of these cores is usually the cache, the L1 cache. Is very, very close to the core that makes it very, very fast to kind of access. Okay. Then we have this L2, the level 2 cache, which is kind of like bigger, but slightly scattered. So it's not like just one unified L2 cache because it's too big. Instead, the trick is usually kind of like dividing this L2 cache into this kind of like, units here. And the reason that you do this is that now, for example, core number 3 can access this L2 cache 3 faster because it's literally closer to the core number 3. So the interconnected, the literal distance between these 2 units is much smaller. As a result, access to that is faster. But since L2 is usually like unified, all the cores usually have access to the entire L2. So it's very possible that, for example, the data that core number 3 wants might end up being somewhere, for example, here. That's why access to L2 may not be kind of like a unified and uniform access latency. It's slightly different depending on where it is. And then things get even worse when it comes to L3 cache, because things, for example, from this core might be very, very close to this. But for example, from this core number 3, things might be farther away. So there are lots of research on the interconnect design and where do you actually kind of slice the data and all those things in order to kind of like minimize this latency. Okay. So this is the story of cache. Usually we do 3 levels of cache on a chip, and everything is kind of stays on chip. That's why it's very quick. Okay. Then we need more data, of course. And that's when we need to, essentially, we can no longer put things inside this die. And the reason is that as the die gets bigger and bigger, building it is much more difficult, mainly because of the failures. Because essentially, if you think about the failure rate as kind of like the function of the area or the diameter, as the diameter goes up, the failure rate significantly grows. As a result, if I want to kind of build like a huge one single die chip, then the failure rate, or in other words, the yield, the amount of successful dies that I'm going to have, it's going to be very, very low. Okay, that's why we usually don't really go higher than specific size. Okay. And as we will talk about in the last week of the class, we're going to talk about this design of what we call chiplet systems. That essentially, instead of like making this bigger and bigger, we find some novel ways of making smaller ones, but connect them to them faster with much better latency. So this is kind of like in this way we can actually kind of grow and scale the systems. But anyway, going back to the original system, this is what we have today. This is the current technology that you cannot really make your cores or dies in general as big as you want. As a result, you need to go off chip. Okay. So so you need to kind of like use the data that you want from an off-chip memory, and this is usually what we have in a DRAM. Okay, so you can have one DRAM or you can have multiple DRAMs, and for communicating with the DRAM, we need some form of a protocol. Okay, this is usually what we call a DDR protocol, and for that we usually have what we call a DRAM or memory controller. Sorry. A memory controller that you can see here, and there's some interface that kind of like send and receive data between the DRAM and the chip. So this is kind of like the general interface of a DRAM and a regular chip. Okay. So DRAM itself, you can think about the DRAM as a gigantic 2D storage array, right? That data is kind of like stored in rows and columns. Okay. So the way that we kind of address the DRAM is that the address comes, okay, and we usually register it into some register. So this is the address registers. And then we have to choose how do we want to kind of like address the rows and columns. Okay, we can do row major or we can do column major. Typically, the most significant bits is going to be used in order to find the row, and then the least significant bits will be used to find the column. Okay, so we have the row decoder that takes the address and choose the particular row. And from that row, then we pick out the column that we want. DRAMs, like any other system, should be byte addressable. So this little, boxes could be as small as 1 byte. But typically, since DRAM is very, very slow and kind of reading and writing from DRAM takes a lot of time, usually it doesn't make sense to just bring 1 byte. Typically, we bring lot of bytes in one go, and this typically is what we do with the size of the DRAM row, which is like 64 bytes. So this is kind of the cache block. And if you remember, a long time ago, we talked about the use case and the importance of having bigger blocks because it reduced the miss penalty and all those things that we talked about a long time ago. So if you look at the read sequence, essentially the read sequence is this 5 stages. So we first decode the row address and drive the word lines. For now, don't worry about the word lines and what they are. I'm going to actually show you another picture to talk about that. Then we're going to select the bit lines in order to actually read the row. Then the whole bunch of like analog activities needs to be done. For example, you need to like pre-charge and amplify and all those things. And then once you're done, you need to kind of like pre-charge again, be ready for the next operations of the DRAM, which again I'm going to talk about but just functionality wise, very simple. The address comes, you divide it into MS bits, most significant bits and least significant bits, in order to choose the block that you want from the DRAM. Okay. So how does exactly this work? So in order to understand the difference between a DRAM and SRAM and generally understand the memory, remember that smaller caches, smaller memories, including L1, L2, and L3, are SRAM based. SRAM is kind of like, you can think about an SRAM as a structure that you see up here. Essentially, SRAM is two back-to-back inverters and then two access transistors. So it's kind of like, looks like something like this, that there are two back-to-back transistors. They're kind of like connected like this. And then these are PMOS and these are NMOS. And the same thing here. And this is where we're gonna kind of like store. So this is VDD and this is ground. And so this is where we're gonna store the data. So the data is kind of like looped into this to this data structure. And that's why this is volatile memory. So as the transistors are shut off, the data is no longer kind of like right here. Then in addition to this, we have two access transistors. These two access transistors actually help us to read these values, okay? And as you can see, we basically read this value here and this value here into these two bit lines. And these two values are usually kind of the opposite of each other. So this is usually we call bit line, and this is the invert of the bit line, okay? And this row that selects these two access transistors is called row select, okay? So for an SRAM, think about it as two back-to-back inverters that kind of stores the data, and then two access transistors that are selected based on the row select. And then we're going to charge this line here and here based on the value that is stored here. For example, if the value that is stored here is 0, then the bit line here, we're going to, charge it to 0, and we're going to charge this to 1. So we actually do it in the opposite direction. The reason that we do it in the opposite direction is that now we can sense the difference better, okay? So when we're doing this, then there is usually a sense amplifier here that doesn't really read this value, but measure the difference between these two lines. And this is how we're going to read this particular line. You had a question? No? Okay. So this is just a general way of the SRAM. And then the big thing about SRAM is that like this transistor needs to drive this line, right? So we need to actually kind of like write and read some specific value to this line. That's why how big this bit line is has a big impact on how fast you can write to the DRAM, what's your noise margin and all those things. That's why you cannot really have a gigantic SRAM, because if you have a gigantic SRAM, it means that you have more lines. So this bit line is connected to many, many more transistors. In other words, you need to push much more load into this line in order to drive it. So it's very, very hard to do that, okay? So SRAM, essentially, the read sequence is we decode the address. The address means that we select one of these rows. There are many, many different rows here, as you can see here. So we select one of these, which is one of these blue lines here, for example, this one. Then this bit cells will drive the bit line. So we basically say that, okay, now you guys are connected and this one is connected too. Means that the value that is stored here now can be offloaded here and here, okay? Then we're gonna, as I said, we're gonna have a sense amplifier to sense the difference between these two columns. And then at this point, we have the data ready. But since this is kind of destroying the value that is loaded here because you're kind of discharging the charge, you need to recharge this line again. So you need to pre-charge this lines again, both this one and then bit lines as well if you need to. Okay, and this is essentially for the next time that you're writing it. Yes.
Could there be a problem because we're using the PMOSs and they pass week 0?
Yeah, so there could be these problems. There are a whole bunch of like designing, like how do you actually design this in order, like, how do you make this design much more? But since this is more of a sense, at the end of the day, they're not really sending ones. There's just a difference between the bit line and that. And usually you don't charge this bit line to 1. You charge this bit line to half of the 1. so that like, you can add a little bit more or you can get a little bit less. So it's kind of like, if you think about like, your 1 is a full bucket and then your 0 is an empty bucket. What you do with the bit line is that you charge it to half. And then you allow the SRAM to kind of either add a little bit to it or chip off a little bit off it. Okay. And then you do it in both sides. So each side is kind of different, right? So whatever you do on the right side is the exact opposite happens on the left side. As a result, you will see a bigger difference. You will see essentially this difference, the amount that you added versus the amount that you removed. So this is how you're going to read this.
Thank you.
Yeah. So this is going to be kind of like how we read from an SRAM. So you get n plus m bits. Oh, sorry, question.
Wondering how big is like the voltage difference?
Oh, very, very, very
So
small.
you have to amplify them later, or-
You have to amplify them, and you have very, very sensitive sense amplifiers. So we're talking about like very small amount. Yeah. Yeah, the whole design of SRAM is very interesting. I'm sure some of your classes, I think maybe 216, or has anybody in any of your classes talk about design of SRAM in your grad classes?
We get like the basic circuit, and we're like, all right, move on,
Really?
pretty much.
So you never seen an SRAM design ever before at UCLA?
I've seen an SRAM design.
No, I mean in any of your classes.
Yeah, but like not.
Not in depth. I see. Yeah, so the design of SRAM is actually quite interesting because you need to kind of like, this is essentially like, how much can be sensed and how much this charge is kind of charge or discharge is telling you how much sensitive your sense amplifier should be. And if your sense amplifier is missing something, this is what we call a noise, right? So you need to know how much your sense amplifier should be able to tolerate noise and all those things. So there are tons of works on DRAM, SRAM design. Anyway, so going back to this, so this would be essentially your quote unquote address. As I told you, we usually kind of like go with the most significant bits for the rows and the least significant bits with the columns. So think about this as kind of the 2 to the power of n row to the power of m columns, right? And usually we kind of like do it kind of a squarish so that, we don't kind of do a lot. You don't want a big bit line or you don't want a big row line. And then what you would do is that you now need to be able to, if you want to read m bits at the same time, you need m of these bit lines, m of these sense amplifiers, and so on and so forth. Okay, so you get that and you get the final value as you want. Okay, a big thing about the access latency of SRAM is essentially steps 2 and 3 is the main drivers of the access latency is when you select the lines and when you let the charge or discharge happens. And then the whole thing is essentially 2, 3, and 5 is the entire majority of your DRAM latency, SRAM latency is 2, 3, and 5. And you always need to do 5 because you essentially kind of like you make it prepared for the next time. If you don't do 5, then next time the first thing you need to do is 5. So it doesn't matter whether you do it 5 now or the beginning of next one. You always do it at beginning of 5. Okay, and then as you can see, for example, the interesting things is like step 2 is proportional to 2m, right? The amount of bits that we have in a column decides how many bits that you how fast you can select a particular row. And then another thing that is important is that the how fast you can charge the split lines depends on the number of rows that you have in your system. So this is a story of SRAM, and this is what caches usually use, okay? So the reason that, for example, L1 is much faster than L2 is for 2 reasons. One is this N and M is much smaller. As a result, these steps are much faster because they're proportional to N and M. So if N and M is smaller, then the latency is lower. The second thing is that the reason that I just showed you that the latency, the connection latency is much smaller. Okay, so these are the main 2 reasons that you see that, for example, L1 is much faster than L2, and that's why we don't really go crazy with L1, because if you do, then our latency drops. But then we go to DRAM, and this is dynamic random access memory. DRAM is much, much simpler design. It's just one transistor and one capacitor. And essentially all it does is that you enable the row essentially, again, just charge or discharge a particular line. And since this is only one transistor, there is no kind of complementary activity here. There's just one, okay? And then the big thing about DRAM is that once you read it, it's completely destroyed, right? So SRAM is usually not destroyed. I mean, you usually want to kind of pre-charge and all, but for DRAM, you definitely need to do it because it's completely discharged or charged. So you have to be very careful when you're reading from the DRAM. DRAM usually use this RAS and CAS. This is row axis and column axis addresses. So we typically, call it this RAS and CAS, and you will see it actually in your, this is the typical terminology for the row and column. And then actually in your computer assignment 3, with the framework you're going to use it, you also will see RAS and CAS a lot. So just keep in mind that it refers to the row axis and the column axis. Okay. So basically steps for reading from DRAM pretty much similar to SRAM. So step 1 to 3 is pretty much the same. The only thing is that the sense amplifier is slightly different because of it's just one-way sense amplifying. And then the big thing about DRAM is DRAM also lose charges even if you don't access it, okay? As a result, you need to kind of continuously refresh DRAM. So after every 64 milliseconds or so, you need to kind of like refresh every line. So as a result, we have this memory controller that is kind of responsible for refreshing DRAMs. That is essentially occasionally go through every row and refresh it. And the big thing about refresh is that as you do the refresh, the DRAM is out of commission. That particular row is out of commission. So you have to be careful about that. And then as you will see again in your computer assignment 3, the whole scheduling is kind of like dealing with these kind of challenges that one row needs to be refreshed. You also need to access it. So how should I do? Can I, for example, not do the refresh and then access it and all those things that we're going to talk about? Okay. So quick kind of comparison between DRAM and SRAM. SRAM is preferable for register files L1, L2 because fast, they don't need refresh. Manufacturing is simpler. It's much bigger. In other words, the density is lower, and the cost is much higher because of the density. But it's much faster, right? So that's why we use it for caches. DRAM is preferable for standalone memory. That's why it's the dominant technology for main memory. Okay. So now that we kind of understand the basics, let's actually dive into the DRAM. So for the next few slides, I'm going to mainly talk about the structure of the DRAM itself. Okay. So DRAM is kind of like within DRAM, we have these different components. We have the channel. The channel is the one that's going to connect the DRAM to the CPU. We might have one channel, we might have 4 channels, and so on and so forth. Then for each DRAM card with this DRAM chip, we usually have DIMMs, okay? So typically most of these DRAMs that we have 2 DIMMs. DIMMs you can think about as kind of 2 sides of the same chip. Then within each DIMM we have ranks, okay? And then usually like, each DRAM has 2 ranks if it has 2 different DIMMs. Within each rank, then we have chips. Let me see if I have, yeah, there you go. So these black ones are your chips. These are literally chips, like, DRAM chips that you put into this PCB, which is this green thing. For example, we usually have 8 chips on each side of a DRAM. And if you have a 2 DIMM, so you have on both sides, so you have 16 different chips, okay? Then we have within each chip, then we have banks, okay? So we have usually multiple banks within a chip. And then within each bank, then we have rows and columns that I just showed you, Okay, so let me actually talk about each of these to you. Okay, so first of all, as I said, we have the processor. The processor is connected to different DRAMs, and this is where we're going to have the channel. Usually you have one DRAM and one processor, so there's one channel system. But you can have multiple of these DRAMs, so you can buy lots of your system might have multiple slots. As a result, you usually have multiple dedicated channels to your CPU. You can also multiplex one channel with multiple DRAMs. That effectively reduce your bandwidth, right? Because you have just one literal channel. But most systems, if it supports multiple DIMMs or multiple slots, it means that it probably has multiple channels. Modern systems has many channels. Typically, your like regular systems has either 2 or 4 channels. Okay. Then, as I said, we have DIMM. DIMM stands for dual inline memory module, which means that you actually, instead of like having one row of like one side of chips, you can have 2 sides. So if you actually like kind of rotate your DRAM module, you will see that on both sides you see chips. Okay. And this is your slots. This is your quote unquote channel. Within each channel, you have a DIMM that goes inside. The DIMM has actually 2 sides. Okay. But these 2 sides share the same channel. So there's no 2 channels per DIMM. Okay. So now if you actually look at the DIMM looks like this. It's actually very narrow and tiny. I'm sure most of you have seen it. Then usually DIMM has a front and a back. Okay, and as I said, in each side you will have chips. Okay, and then which side we call it the rank. So usually like the front side we call rank 0, and the back side we call rank 1. Rank is important because it helps you to kind of address. So for example, if you want to address one particular chip, you need to know whether this is the front or the back. In other words, whether this is rank 0 or rank 1, and then which of these chips is there, right? So rank is important in order to address. So part of the address, you have to actually define which rank you are using. Then within the rank, we have the address. So for example, as I said, you can think about that, the address comes, okay? Usually we have this thing called chip select, CS, and the chip select whether rank 0 will be selected or rank 1 will be selected. Within that, let's say we have a 64-bit data or address that's coming up, okay? So typically the address goes to both ranks, but the chip select is the one that tells whether it should be rank 0 or whether it should be rank 1, okay? So now let's look what's going on in each rank. So let's, for example, look at rank 0. As I said, we have 64 bits that goes inside each rank. Within each rank, we usually have multiple chips. Typically, we have 8 chips, and each chip is actually putting out an 8-bit data, okay? And so, for example, chip 0 contributes to 8 bits, chip 1 contributes to the next 8 bits, and so on and so forth. The reason for this is that we want parallelism, right? So you don't want everything that goes into one chip. You want to be able to kind of like push out data from all the chips at the same time. So that's why you have multiple chips, okay? Within each chip, then we have what we call a bank, okay? Typically, we have 8 banks within each chip. And this is where we're going to actually have multiple different data. So you're not going to do 1 bit from each bank. Actually, all of them provide the 8-bit. But the nice thing about banks is that you can read different addresses from the same chip from different banks. So bank allows you to parallelize between requests. Okay, so this is an important thing for each of these banks. So we usually have 8 banks in the system. Then what do we have in the bank? Within the bank, we have that 2D array that I showed you. So a DRAM at the end of the day becomes a 2D array that has rows and columns. And that essentially is just one of those banks, okay? But we have multiple banks, multiple chips, and multiple rows, multiple ranks, and even multiple channels. So this way we can have a gigantic memory system. Yep.
Where is this usually amplified?
Amplified as in?
So you talked about how the signals of on the actual DRAM cell is very, very small.
Uh-huh.
So where in this process is it amplified to?
Oh, this is within the bank. So now I'm actually getting to that point.
Oh,
So within the bank, you have actual a DRAM cell, the actual cells. Okay, the actual cells is within the bank. Okay, everything else is just concepts. There's not really a physical system to it. Okay, so within the bank, we have rows and columns. Okay, the big thing about DRAM is this thing called row buffer. Okay, so when we are actually reading a row, okay, we put it into a buffer called row buffer. Okay, and row buffer is typically really big. Okay, so we usually have 2,000 bytes, 2K bytes. The regular size of a row buffer is that. Okay, and then each column in each kind of like block in this row buffer, you can think about it as 1 byte. Okay, that's why it gives you 8 bits outside this. So essentially, within the row buffer, the block that you choose that will give you 1 byte of data. Okay, so each column essentially, like each block within each column within this row buffer is 1 byte, and we typically have many rows. The number of rows usually decides the size of your bank, right? So for example, if one bank is supposed to be 1 megabyte, then you can do the math to find the number of rows. Okay. So how do we actually transfer data? So for example, let's say we want to read 64 bytes cache block. Okay. So remember I told you that usually we go 64 byte. So this is how we're going to do it. So we're going to essentially read 64 bits together. Okay. So how do we do that? We, for example, select. So let's say we have one channel only. So in order to read that, we select one of the ranks. Let's say rank 0 is selected. As I told you, the data is provided by all the chips simultaneously. So chip 0 is 1 all the way to 8 to 7, provides bits from 0 to 63. And then within each, they actually gonna select the row that they want and then bring out the block within that row that they want. Okay. So for example, they would do row 0, column 0 for all of the chips. Okay. And then bring the data out. And this would be 8 bytes of data. And that will go inside the first part of the block. Since this is a 64 bytes, I need to do it multiple times in order to get the 64. Okay, so I need to keep repeating this for column 1, column 2, column 3 in order to eventually get my whole 64 bytes. So I need to repeat this 8 times to transfer 64 bytes. Okay, so any 64 bytes, in other words, are 8 consecutive IO transfer from the main memory to your cache. Okay, just keep that in mind. All right. So yeah, any questions so far? Yeah.
What is the function, sorry if I missed it, of the buffer for each bank?
The row buffer. We're actually going to get into it, but keep in mind that if I go back here, selecting rows takes a lot of time. Okay, so selecting a row and bringing data to the row buffer takes a lot of time. So what we do is that if we anticipate that if I read this byte here, very soon I'm going to read this byte and this byte and this byte and this byte. What I can do is that I can retain the data inside the row buffer. In other words, I don't close the row buffer. I keep the row buffer open. Okay. As a result, the next time I'm reading this, I no longer needs to activate the row and read the columns. I just directly read it from the row buffer. In other words, that's what we call row buffer hit. We're going to actually get to it, but row buffer hits gives you a huge performance boost. And exactly that's what you need to do in your computer assignment series, that you need to maximize your row buffer hits.
Okay, thank you.
Yeah. All right. So as I said, a DRAM. Sorry about that. 1, 2, 3. Seems to be working. All right. So the DRAM, as I said, eventually comes down to a bank. The bank, you can think about it as a 2D array of rows and columns. A row, usually we call it the DRAM page or a DRAM row, okay? The sense amplifiers, the like where we actually do the amplification and all that also happens in the row buffer. So you can actually have two ways of accessing the DRAM. This is what we call a closed row and an open row policy, okay? So what is a closed row? The closed row requires three main activities, okay? So when an address comes to a bank, okay, we first need to select the row. So we need to go and bring the entire 2 kilobytes of data into the row buffer, okay? This is what we usually call activate, okay? So we activate that row. Then we read that value to the row buffer, okay? And then we kind of transfer that data back to the CPU. And then we just pre-charge the row for the next access, okay? This is what we call a closed row. So we essentially read a row, write it to the row buffer, takes the block that we want, and then write the data back to the row, pre-charge it, and close the row. So the next time, even if the data is in the same row, we need to repeat this three-step process, okay? The alternative to that is we don't need to, we don't need to keep reading the same row over and over again. Instead, what we do is that if this is my 2D array, I'm going to, for example, let's say read this and write it into my row buffer, okay? I don't close the row, which means that I'm predicting or anticipating that this same row is going to be used in future again. Next time the addresses comes, it is in the same row, then I don't need to activate anymore because I already read this row. So I just bring the next block and read that block. In other words, I'm saving on the activation command, which is actually quite timely and time consuming, okay? So the difference between closed row and open row is that you don't close the row buffer if the next address comes. But what do you think is what is the disadvantage of this approach? Anybody wants to? What's the disadvantage of closed row, open row approach?
This, you have to pre-charge and reactivate, which is a longer than.
Yes. So if you miss, now you have to pre-charge back the row that you opened. Now you need to open a new row. So you essentially pay more penalty because of that, right? So if you have lots of row buffer hits, in other words, you have lots of spatial locality, then it makes sense to have an open row policy. But if you want to be really low power, then it's a good idea to have a closed row policy. Okay, so this is kind of the trade-off between the rows that we have. Let me do this example for you. So let's, for example, say that we have this sequence of addresses, okay? So for example, we have row 0, column 0, row 1, column 1, row 0, column 85, and row 1, column 0, okay? So as I said, the first address comes, we will select row 0, okay? We're going to bring this row 0 to the row buffer because that's the first time that we bring in this data. So we need to put it into the row buffer. And then we're going to pick out column number 0, and that's it. Okay. Now the second row comes, and if this is an open row policy, if this is open, the nice thing that will happen is that once row 0, column 1 comes, I no longer need to read this again. I already have it in the row. In other words, we have what we call a row buffer hit. And then what I do is that I bring the second column and push it into the data, okay? Then 85 comes, and then again, I'm going to have it here, and I'm going to read it. Remember that this is usually 2K. Okay, so the row is pretty big. Then this row 1 comes, and then I see that, oh, this row is not actually there. So I need to write this back. Then I need to write this into the row buffer and then bring out the column 0 of that. So it's a slightly more time because of this, versus if I didn't have the row open policy, I would have had row miss here, but this last one would have been faster, right? So this is the trade-off that we need to deal with. And sometimes it's a good idea to have an open row policy, sometimes it's not. Okay? Let's have a quick break and then we're gonna come back and talk about this. Let's continue. Everybody's a little bit rusty, I guess. We haven't had.
Yeah.
All right. So to kind of summarize the basic DRAM operations and latency, and this is actually the part that you're gonna see a lot in your computer assignment 3, is essentially the DRAM operations boils down into these different times. Okay, so of course, first the request should be initiated by the CPU. So this is the transfer time. This is just a regular latency between CPU and DRAM. Then you're going to have the controller latency, and the controller latency is the time for scheduling various different requests. Because keep in mind that there are multiple cores and there's only one DRAM. So there are multiple requests comes at the same time, but the DRAM may not be able to request all of them at the same time. So there is some form of queuing happens. There is some decision making and scheduling needs to be made. Okay, that's why not all the requests will be immediately serviced. They might be queued and not be serviced for some time. And the scheduling now here is very, very important. And again, your computer assignment 3 is all about this scheduling. Like, how do I choose which request to service first? And given that decision, then the amount of time it takes for all the processors will be different. Okay, so essentially what happens is that the controller needs to make some decision, and the decision itself might also take some cycles. So for example, you might use a fancy, I don't know, machine learning based decision making process, reinforcement learning based decision making process, which itself, it might take 1 or 2 cycles. Okay, so that's another thing that adds the latency. All right. Then we have, once you make the decision, now this is the action time. The action also takes time. How much time does it take? So the time it takes, it depends on what happens. Okay. If the row is already open and you have a row buffer hit, the time it takes to access this is the column access time, or CAS. Okay. If you need to pre-charge the array, then you need the row access time and the row CAS time. Okay. If you need to pre-charge the previous row and then do the row read, then it would be the pre-charge processor as processor CAS. So essentially, the difference, as you can see, is that this is the open policy with row buffer hit. This is the closed policy, which with no row buffer hit or miss, and this would be with the row buffer policy with the row buffer miss. Right? So this is the difference. As you can see, if you had many, many misses, then essentially you're paying this pre-charge extra time for the open policy. But on the other hand, if you get lucky, you only pay the CAS time and not RAS plus CAS, right? So these are the difference between the decision making that you need to do. And of course, once you get the data, your data needs to be still transferred back to the CPU, so there will be another transfer time from DRAM to the CPU this time. Okay, so together this would be your latency, your end-to-end latency of your DRAM. Okay, and of course, in order to boost your performance, you need to make this as fast as possible. If you remember, in the cache, we defined this as average access time, and we told you that, oh, this is the hit rate plus miss rate times miss penalty. And we told you that miss penalty of last level cache is the latency of this DRAM. So this is exactly that. Okay, so the lower level of your cache miss penalty is this number. So if I reduce this, I effectively reduce my AAT. In other words, I'm improving my performance, right? Another big thing about DRAM is power. Okay, so power consumption is also a big thing in DRAM because these things happens a lot. So another thing that you will see in your computer assignment is that we want you to also minimize power. In other words, we will ask you to not only just reduce latency, but also reduce power. In other words, we want you to reduce energy delay product. So you have to minimize this number in order to achieve the best possible system. Okay, so reduce energy, reduce delay, and then together you're going to have an EDP, a minimized EDP. And of course, sometimes reducing performance will increase the power, or the other way around. You can do reducing power, but your performance will take a hit. So here you have to now play with this trade-off game that, okay, this will save a lot of power, but only decrease performance a little bit. So its overall EDP is beneficial. Okay, so in this particular computer assignment, so you'll see a little bit more of kind of design and engineering in your system, that not only you just improve performance, but you try to improve the power as well. Okay. So give you some numbers to see the difference between open and paid, open and closed. So for example, if you have an open policy that we keep the row open until we see a conflict. If you have a row buffer hit, we usually have cache delay, which is typically in the order of like around 10 nanosecond, 12.5 nanosecond. If you have a conflict, then we have to pay pre plus RAS plus CAS, which is around 37.5 nanosecond. On the closed page policy, we only pay RAS and CAS all the time, so it's around 25 nanosecond. And yeah, that's essentially you're talking about these two numbers versus this number. And then in order to see which one is beneficial, of course, it depends on how many hits you get. So your row buffer hit rate is the important factor here. Okay. So now that based on this, the big question is, how do we schedule when to close the row? Should we always go with close? Should we always go with open? What's the best way to do it? And let's see what sort of ideas you guys have. How do you think we should go about this? This would be the first steps of your design, basically.
Could you do some sort of implementation where you're monitoring your hit rate, and then if it goes like too high such that the delay is longer than the closed page policy, then you switch to the closed page.
Yeah.
Default stay with the open.
You default stay with open, yeah, and then go to the close, yeah.
We do memory paging, so we would know that cache block was within the page. So then we could like default always open page. Stuff that is within the page table and that we need to get into the cache.
I mean, you would start with page, but what if you don't really access multiple cache blocks within the page? You might kind of just jump around multiple pages. That's where you're not gonna get benefit from your open row policy, right?
Right.
I mean, by default, you kind of expect to see, but remember that we had thrashing algorithms, cache unfriendly algorithms. The same thing, kind of like translating to this, right? You have row buffer unfriendly applications and row buffer friendly applications. And then, so this is kind of like, in order to decide open and close, right? So you have to use some form of dynamic, maybe try a little bit of debugging first or profiling phase, and then make a decision, right? So these are the options that you have. The second question now is about scheduling. So for example, there are 4 different requests comes from 4 different cores, okay? Which one do you think we should schedule first? What are the policies you think we should use? Any suggestions?
Most naive one is FIFO.
FIFO, yeah, first come, first serve. Yeah, first come, first serve. Whoever comes, we just yeah. Anything else?
Check, there's a hit and there's a hit through stoppers.
So we see if we maximize our row buffer hits. So whoever gets the row buffer hits, that goes first. Okay. This is we usually go the first ready kind of thing. Anything else? What would the problem with this?
That's increasing the delay to check all of the cores
Mhm.
before you make a decision.
Yes, okay, that's one thing, but it might save you because you get row buffer hits. What other problem this might have, other than checking all the cores?
You just keep hitting on the same core so that other cores can't process it.
Exactly, so you get lots of unfairness because one will hog all the kind of like requests because you keep like, especially if one that's like really doing a good job on row buffer hits, you keep like servicing that core, the other cores quote unquote starve because poor guys don't have the row buffer hit and they have to wait, and that will diminish their performance. So what can we do to fix that?
You should do like round robin where you just swap between them.
Redo round robin, so you like you just one at a time, but you will sacrifice your row buffer hit, right? So you're not gonna have a good row buffer hit. But if you do round robin, do you think then closed policy would be a better option than open policy?
I mean, I guess because with the possibility of not having a rubber hit, then yeah.
But how? Yeah.
Oh, I was just gonna say, for the other one that we talked about, like first ready, you
Mm-hmm.
could do, so like if you notice that there's like a starvation problem, you could preempt that
Mm-hmm.
and then service the other core.
Mm-hmm.
To have a maximum like number.
Yeah, so it's kind of like at some point say that, oh, okay, this is enough, then I need to really kind of like have some deadline or yeah. Any other suggestions? Good, I think you have now you have enough ideas for your computer assignments, right? So these are all these things that you said are good. So we can have, for example, first come first serve or FCFS, which essentially just you do the oldest first. That's kind of guarantees fairness, in other words. You can do first ready, first come first serve. That you say that okay, let's me try row buffer hit first, and then if there is no row buffer, then I'll do the oldest next. And then there are a whole bunch of other version of this FRFCS, which, for example, you have a deadline that you time out, you have watchdog timers, you combine this with some round robin and all those things. And then all these things also depends on the policy of if you're doing open policy or doing a closed policy. Because if you do closed policy, then you probably want to do more of a round robin first come first serve approach, versus if you do an open policy, then you may want to somehow bring out the row buffer hits. Okay. So these are actually kind of like things that you need to be careful about. Yeah.
Is it possible to do preemption for RAM access? So in the middle of reading, you just switch to a different.
You can, but usually it's doesn't make sense, right? So you want to finish, usually do one command at a time and you wait for that command to finish. Otherwise, you're wasting energy, right? If you're writing, you have to be very careful because that could cause, disruption to the data and inconsistency to the data. But for read, yeah, you can cancel in the middle if you really need to. But usually it doesn't make sense to cancel in the middle because then you just waste the energy. So you actually get some idea of the consequence of unfairness. This is actually the time, the normalized time, stall times for the processor. As you can see, some processors might have actually see up to 7 times slower performance if you really not be careful about this furnace problem. Okay, so things might get better, but some others might get a lot of latency. In fact, this itself could be an attack. So it could be what we call a denial of service attack, where one particular process, creates the access pattern that has lots of row buffer hits. As a result, every other process kind of starves to death, right? So usually most of these modern systems are careful about like the way that they handle this. Okay. Yeah, so there are a whole bunch of things that one can do in order to improve this. For example, you can try to have row buffer locality. You can use the parallelism. You can try to have a fair scheduler, as we talked about, such as make sure that you have some preemption or some additional decision making on dynamically to make sure that not all the requests just goes to one core. But of course, these things also reduce your performance. So reduce the performance of the main core, and the other cores will be affected as well. So you have to be very careful about this. I'm going to let you guys kind of like spend a little bit of time on your computer assignments and come back with questions if you have about this. But you will see a lot of these interesting trade-offs when you actually start designing your system. So as I said, there's round robin, and as I told you, the power is also very important. So not necessarily you always improve for performance. Sometimes you also optimize for power, which means that, for example, the amount of pre-charging, if I can minimize the amount of pre-charging, I'm going to save a lot of power, right? So power consumption also kind of play a role here. So you have to be not only just say that, oh, I'm going to pick the method that has the best possible latency, because that might result into lots of additional pre-charges and all, which not be beneficial in terms of power. But as I said, you will see a lot of these kind of trade-offs in your computer assignments. All right. Questions? Okay, so to summarize, this is kind of your memory system. So you have the request comes from the memory controller, goes to the channel. The channel has a bunch of DIMMs. Each DIMM has a bunch of different chips. Within each chip, you have a bunch of different banks. Within each bank, you have rows and columns. Within each row, you have a bunch of columns. Each one is a cache line in your system, right? So this is kind of like, just a quick summary of things that we said, that, banks shares the address and data bus. A chip has multiple banks, so there's no difference between the banks, right? But chips can act independently from each other. That's why we actually have, we divide the data into multiple chips. And then, as I said, multiple chips creates a DIMM, and multiple DIMMs create a rank. And in each chip always have 8-bit interface. Just remember that, right? So we always like push out 1 byte at a time from each chip. Okay. So what's the point of having multiple banks? So multiple banks will enable concurrent accesses, okay? Because essentially banks can provide a different set of bytes, okay? So a good thing about bank is that if multiple requests comes to a particular chip, then it can be applied to different banks, and each bank can independently provide the data. So although the channel is just one channel, so I cannot send all the data at once, I need to still serialize it. But keep in mind that I need to pay the price of pre and RAS and CAS, right? So what can I do is that I can overlap this request, right? So if I can kind of like, access banks in parallel, as one is doing the pre, the other one can do the RAS, the other one can do the CAS. So kind of like I'm kind of hiding this latency into the system. So as you can see, for example, if I have, a bunch of different addresses, A0, A1, A2, so wait for the DRAM, gets the data, wait for the DRAM, gets the data. I can actually, if I somehow all maps into different banks, then this one comes, goes to one bank. Immediately, this one comes, goes to another bank. and then boom, boom, boom. I'm gonna get the stream of data much faster after just the initial time. Then the banks can kind of just give me the data as soon as they're ready. So essentially, the bottleneck just becomes the channel itself. It no longer needs to wait within the internal of the DRAM to get the data. Data is always ready at the chip level. I just need to push it out through the channel and send it to the core. Okay, so this is the beauty of having multiple banks. So it can gives you a very fast communication. So in other words, increase your bandwidth. It doesn't change the pure latency, so the latency stays the same, but you can push out more data if you want to. Okay, but of course, this means that you need more wires. You need more hardware. You need more power because now more powerful things happens at the same time, and so on and so forth. And then the last thing I want to talk about is that given that this banks give you this parallelism, the idea is that how can I actually interleave my addresses such that they map into different banks? Because if I can map them to different banks, I can map consecutive addresses to different banks, then I'm going to have lots of these bank parallels. Okay, so this is where we're going to need to think about how should I kind of assign the mapping of a 64-bit address to my system. So for example, I can have something like, the bytes in the bus, the column, the bank in the row, or alternatively, I can have something like, oh, the column is like, divided into two parts and the bank is somewhere in the middle. And this way I can kind of like make sure that the banks are more kind of scattered. The first one is usually what we call a row interleaving. Okay, so we kind of ensure that each row is kind of interleaving to different banks. This one is usually what we usually call a cache block interleaving. So we kind of like make sure that the blocks within cache is mapping to different banks. Which one is better depends again on the system. Usually this is hard coded into your system, so it's not something that someone can change. But just keep in mind that the way that we map these addresses into the rows and columns and banks has different impact on how much performance we're pushing out of our DRAM system. Does that make sense? Okay. Yes, and then you can even do this more randomized, so you can even have like some form of an XOR or some hashing algorithms to even further randomize this. So instead of just taking this 3 bits and say that, okay, this is deciding which bank, you can kind of like say that, okay, I'm going to XOR this together with some other random bits, so and then assign it to a bank. So in other words, I'm kind of trying to normalize or create a uniform distribution of this bits. If you remember when we had branch predictors, we kind of had similar idea. Similar ideas are actually being used here. Okay. And then one final thing before we jump into Rowhammer is DRAM refresh is a big challenge in all of these things that we are talking about. Okay. So the problem with the refresh is that the capacitors of each individual cell leaks. So you have to actually, refresh every single cell after a few times, okay? So you need to periodically do that. Typically, this is 64 milliseconds, but different technology is slightly changing. The implication of DRAM refresh on the system is that you do refresh at the bank level. So when you're refreshing a cell, you cannot use that particular bank. The good thing is that you have multiple banks, so if you manage to refresh a bank while the other banks are in use, then you're essentially hiding the refresh time, right? But if the bank that you want to use happens to be at the same time that you're refreshing it, then you have to stall. You have to wait for the refresh to finish, okay? Another thing that you have the option for is you can either burst your refresh, so you can say refresh for all the banks, or you can refresh one bank and then service some requests and then refresh another bank and so on and so forth. The difference between them is, the scheduling is a little bit different. So again, in your framework, you will see that there is a refresh in the simulator. You have to also work around that refresh in order to make sure that your system works. Yeah.
I think for the last slide, when you were talking about making like an even distribution
Mhm.
for all the banks. Like, how beneficial is that? Because if you only have 8, they're gonna get full anyway pretty quickly, right?
Full
I
as
mean,
in,
not full, but like you can't, I mean, you're gonna be they're gonna be servicing different like requests.
uh-huh.
And if you only have 8,
Mhm.
does it really help to have a random distribution?
Yes, because I can, so regardless of how many I have, as long as I can just overlap them like this, then I'm good. Like ideally you want 8, if you have 8 requests, you want each one to be assigned to a different bank,
Oh, okay.
right?
Yeah.
Yes, if you have 9, then one will go into one of those banks, but you can also think about that request comes scarcely, like it doesn't come like one after another, right? So as you're servicing one, the funds finish, the other one comes. So if you have enough kind of distribution, you actually can hide all the kind of time in a system. And then another thing that you need 8 is because remember, each one provide 1 byte. So 8 can give you an 8 byte, and 8 byte is the number that you're usually looking for, like the 64-bit. So that's why 8 is usually a good number.
Okay.
Yeah, so this is the difference between distributed and bursty. And the bursty one cause a long pause, but it gives you a long period of doing just scheduling and don't be worried about the refresh. Versus the distributed one is kind of occasionally kind of refresh the system. So you have to kind of dance around it. So both you can do. The nice thing about DRAM refresh is that typically you can postpone DRAM refreshes if you need to, but there is a hard deadline of 64, so you cannot postpone it after that deadline. But within that time frame, you can issue the refresh whenever you want. Okay, so that's kind of like an important kind of metric that many these schedulers use to decide when is a good time to refresh, and you will see that in your projects as well. Okay. Questions? All right, so let me talk about the security as well. So the main thing about DRAM is, what if someone can flip random bits in my DRAM? Okay. And to think about this, how this could be possible, this could be possible by physical attacks, okay? That one can actually change the environmental condition of the system in order to do that. The main example, the one that's like kind of these days have lots of attention around it, is the problem of what we call a row hammer. Okay, most of you probably know what the row hammer is, but the basic idea of row hammer is this very, very, very weird behavior of DRAM, which if you write to one row, then adjacent rows to that row is impacted as well, just because there is some form of electrical coupling between rows, that if you keep accessing one row, these two nearby rows are kind of leaking. So the leakage speed of these nearby rows speed up as you kind of keep writing to the row. So here's what happens. So let's say you have a DRAM organization like this. As I told you, we have multiple banks. Each bank has a row, and each row has multiple cells, right? So this is, for example, row number 0. Okay. The problem, as I said, is that each row, each cell has some structure like this, that generally this leaks. Okay. And so if this word line is somehow getting a little bit higher than 0, then it kind of is as if that you're opening this a little bit, so you're allowing a little bit of charge to just discharge. Okay, that's really what's going to happen. So essentially, what will happen is that generally over time there is a leakage for each cell. So if you think about this, that's kind of like the voltage of the capacitor. Over time, this voltage kind of like gradually goes down. And this Vmin is the amount that you can allow this voltage to go down for this cell to still be read as 1 or 0. So what we do with refresh is essentially we recharge this cell so that it goes back to the 100%. So as long as this time is not below, so the amount of discharge does not go below this minimum, we are good to go. And this is what we define as the refresh window, and that's 64 milliseconds, kind of like based on this. Okay, it's based on how much can we allow the voltage to go down, and as a result, how long does it take for that voltage to go down to that point. The refresh should be happening faster than that. Okay, so that's the basic operation of a cell. As long as we do this refresh, we are good to go. Okay, but what happens with the row hammer? The row hammer essentially is this issue of opening a row that impacts this nearby row. So if I open this row, okay, and open and close this row, remember that I need to pre-charge this row over and over again. Okay, as I do the pre-charging, what will happen is that this nearby rows, first of all, this is what we call the adjacents, and people have recently shown that the blast two, like the 2 rows from the main row, is also impacted by this. So these 4 rows, quote unquote victim rows, are impacted by this. So what happens is essentially what used to be this, that you kind of expect that this is the kind of pattern of discharging. If I close and open this row, now if I look at row 1, I'll see something like this. That essentially if this was kind of like going like this, if the attacker row keeps being opened and closed, I will see a jumps in my discharge. Okay. As a result, by the time that I was supposed to refresh, my voltage is at this point, and at this point it no longer can be recovered back up, because at this point the refresh thinks that this was indeed 0. So it's actually after refresh it goes even further down. Okay, so what used to be 1 and supposed to be like this and then goes back up and then goes like this, now will go directly to the 0. So essentially by writing to an adjacent row, I'm depleting a nearby capacitor and flipping the bits on that capacitor. Okay, this is what we call row hammer. Essentially, what happens is that you're hammering this row. You keep accessing this row. This doesn't happen one time. You need to do this 1,000 times. But keep in mind that you have a lot of time. You have like 64 milliseconds to access that row. So you keep accessing that row, and what will happen is that these other rows will flip. Okay, and you might wonder that why do I want to flip those bits? The reason is, for example, this row may not belong to you. So rows are for different processes. Each process has their own rows. They cannot access other rows because of the principle of isolation, right? So the attacker cannot directly change values in this row. They can only change value in this row because this belongs to them, okay? But it happens to be mapped next to a victim row. So as I just kind of like, innocently just reading and writing to my own rows, I'm actually impacting the victim. Okay. Questions? So row hammer, of course, won't be successful all the time. So for example, this black one is destroyed. This blue one is also destroyed. But if the amount of leakage is small, then this green one will be recovered. Okay. So it doesn't mean that row hammers can be able to flip all the bits. It can flip some of the bits, but cannot flip the others. Okay. But keep in mind, only 1 bit is enough for security purposes, because that 1 bit could be very, very, very important bit. Okay, so people can flip just 1 bit and do very, very, very dangerous attacks to the systems. Okay, so there are a whole bunch of challenges, and part of your paper readings next week and paper presentation is going to be talking about this. So for example, how do I find the address mapping? How do I skip the row buffer hit? Because remember, I need to do lots of pre-charge, right? So I cannot just access things right after another and think that I'm doing row hammer, because if it's row buffer hits, there is no pre-charge to that particular row. I want a lot of pre-charge to that particular row. So I need not only find the right addresses, but I also somehow needs to kind of skip the row buffer hits. So from the attacker's perspective, row buffer hits is a very, very bad thing. Okay. So how do I do that? How can I actually speed up this process? This is what we call a single-sided versus double-sided. So if I from this, I can, for example, in order to hammer this row, I can, for example, control this row and this row together in order to flip bits in this row number 1, or I can just write into this row number 2 and then try to flip bits in row number 1. This is what we call half, one-sided or two double-sided. So I can actually be very, very powerful, kind of sandwich a victim row between two aggressor row. And that's one possibility to attack the system. And of course, there's a big question of, okay, I flip a bit, now what? What can I do with it? And there are lots of papers shows that, for example, we can do things such as privilege escalation, right? If there's one bit that decides whether you're root or user, if I can flip that row, then boom, I'm now become a privileged user of that system. So there's tons of works that shows that you can actually, if you flip the right bits, you can do very powerful things with it. The research in Rowhammer, of course, now it's kind of like twofold. There's tons of new attacks, and as you will see next week, you will see interesting papers of like innovative ways of doing Rowhammer. The defenses essentially is that how do we protect this? And defenses are kind of like divided into different categories. There are software methods in order to protect the memory. There are error correction methods that even if some bits are flipped, we still can recover. There are prevention methods such as, let's change the hardware, let's refresh faster, let's do these kind of things. And there's also like directly changing the hardware. Like, for example, let's move the rows after a while. Let's have some thresholding mechanisms and so on and so forth. Again, we're going to see a lot of interesting discussions, hopefully next week when people are going to present papers about Rowhammers. Here, I'm just showing one possibility. So let's say, for example, you have an aggressor row that attacks two victim rows. You can actually try to kind of refresh this nearby rows, and that's kind of fix the problem. But as you refresh, then the refresh itself has negative impact on the next row. So what people, for example, have suggested is if I see a lot of requests to one row, what I can do is that I can what we call row swap. So essentially, it takes a row and move it somewhere else. Okay, because remember, in order to flip bits, I need to do lots of pre-charge. So after a few pre-charges, I just move it to somewhere else. So it no longer can have negative impact in these victims. It will have negative impact in these victims. But if I keep moving this aggressor row to different places in my DRAM, I kind of never let to actually exceed some threshold, right? So you see a kind of potentially problematic row, but you keep moving this and bouncing around in the DRAM that never actually have enough time to impact any particular row. Okay, there are a whole bunch of other solutions. You can see it next week. Okay. Questions? Yeah.
Isn't that last one like really hard to do?
Well, why it's hard to do.
You'd have to read it out of one row and write it into another and then continue your regular operation.
Yeah. That's what you do. Yeah.
And that would take a while, wouldn't it?
It happens in the background, right? So you don't need to do it. So all you need to do is like issue another write, right? So, and then if that write is not part of your critical path, who cares?
Mhm.
But yeah, this is I think it's one of the papers actually going to be presented next week. So we're going to see. Any other questions? Okay, so yeah, last slide. So this Rowhammer is actually part of a bigger class of problems, and these are problems that we usually call fault attacks. Essentially, the idea of fault attacks is using some physical phenomena in order to create some form of bit flips or some form of errors or faults in the system. Hammer is the great and the most popular example of it. But people, for example, have shown that if you have a very strong magnetic field and put it close to a device, it might flip some bits on the disk. Okay. Other people have shown that if you change the voltage or the frequency of the device, that will also cause some bit flips on the system. So there's tons of these different ways, usually changing some physical parameters in order to create some faults into the system. And all of them cause some form of bit flips either in the memory or on the processor, on the way between the memory and the processor. So in order to make sure that your system remains secure, you need to be very, very careful about where bits can flip and how we can protect the system from being attacked like that. Okay. Yep, that's it for today. Wednesday, we're going to have another lecture. We're going to talk about memory safety. Okay. Thank you.